Happy Pi Day, everyone! In celebration of this most mathematical of all holidays, we are going to explore that strange intersection between math and horror by estimating the value of pi using bones. Well, it is indeed Pi Day. I have my pie shirt. Dr. McCoy has his pie. It's a day for celebration for all of us mathematical nerds. If you've been around this channel for a while, you know that I like to take a moment every year on Pi Day to find some way to celebrate Pi Day and to celebrate mathematics, while also staying true to this channel's dedication to horror. And I think I've got a great one for you this year. But before I get to that, I also have to mention we're not just celebrating Pi and Pi Day this year, but today is also the release date of my new book, Arithmophobia, an Anthology of Mathematical Horror. Of course, this book had to come out on Pi Day, but if you haven't got your copy yet, don't worry, it is still available for order. So if you haven't already got one, I will love you forever if you go and order as many copies as you can possibly afford. There's links down in the What's It where you can find all the information. You can get it from me at polymathpress.com, and I'll be happy to sign one for you. It's also available wherever you like to get your books. And if you like this intersection between math and horror, you're gonna love it. Okay, commercial over. Let's talk about today's little experiment. Pi, not the food, but the mathematical constant, is of course the ratio of a circle's circumference to its diameter, and it comes out to approximately 3.14159 and so forth. But it also has a remarkable tendency to show up in all kinds of unexpected places all over mathematics. And today we're going to be able to estimate pi not by measuring a circle, but by casting the bones. Now, of course, casting the bones really has nothing in particular to do with mathematics. Also known as osteomancy, casting bones is a form of divination in which one throws bones onto a surface and attempts to read meaning or to predict the future based on the pattern in how they land. Different forms of bone divination have emerged in numerous cultures all around the world. The Chinese, the ancient Chinese, had a form of bone divination. It was popular in the Shang dynasty, which ran from about 1600 to about 1050 BC, in which the diviner would burn cattle bones and interpret the cracks that would form. The particular form of bone divination we're most familiar with, and the form most similar to our upcoming experiment today, involves throwing small bones on a hard surface, and it seems to have originated in various regions of Africa and come to the United States, probably originally through the slave trade, until it eventually manifested in voodoo and hoodoo religions, and is still practiced by some people today. So that's our connection to horror. Divination, bones. And our connection to mathematics, of course, is we're dealing with pi. What we're going to do today looks a lot like osteomancy, but instead of predicting the future, we're going to try to divine the value of pi. This has, of course, become a Pi Day tradition for many mathematicians, whether professional or recreational mathematicians or math nerds of all varieties. Every Pi Day, we like to come up with some interesting way to calculate or estimate the value of pi. And instead of mystical reasoning, we're going to use math for our little divination, which, to be fair, math does look a lot like magic until you sort of peel back the curtain and look at the proofs underneath. Not to worry though, we're not going to go too deep into the mathematics. We're going to keep things on a level that I think everyone can still enjoy. Unfortunately, I only have a small number of the kinds of real little bones of the sort that I would need for this experiment. So instead of real ones, I'm using these plastic ones. These little what are these, a couple inches long. That is actually going to work to our advantage because we want them to all be the same length as each other for the math to work out. Doesn't really matter how long they are, but they should all be the same as each other, and these of course are mass produced. They are the same as each other, and these are the ones that I happen to have lying around because of course I'm the kind of guy who has little bones lying around. So how's this going to work? It's based on a famous discovery in mathematics called Buffon's needles. Instead of needles, I'm just substituting these bones, but the math is going to work out the same way no matter what long, skinny thing we use in place of a needle. I'm going to explain briefly how it works now, but if you're interested in going deeper with the mathematics, I'll link you to some resources down in the What's It. The proof isn't really difficult per se, but you do need to know a little bit of trigonometry, a little bit of probability theory, and then you need to evaluate a couple of integrals, which is not all that hard for a mathematician, but is a bit beyond the scope of what we're doing here on this channel, because this is of course a horror channel rather than a math channel. What we really need to know is that we're going to use this grid, and the probability of a bone intersecting, or a needle intersecting one of these lines, that probability comes out to 2 over pi. You'll have to take my word for it for the moment until you see the proof, if you want to see the proofs that I've linked in the What's It. But the practical experiment becomes really easy to do. We're just going to throw bones and measure how they land. So what we do is we draw this array of lines spaced the same distance from each other as the length of one of these bones. You can see that these are equidistant, and their width of each section is the length of one of the bones. We then throw the bones onto our array of lines, and we're going to count up how many of them intersect one of the lines. And so, just to clarify, this is obviously not intersecting a line. This is intersecting a line. Even if it intersects just a little bit, that counts. So we're going to count up how many of them intersect any of these lines. And then, knowing how many we threw in the first place, we find the proportion of the bones that intersect any line, and that ratio should come out to be equal to 2 over pi. We can then rearrange that equation p equals 2 over pi, we can solve that for pi, and we'll get pi equal to 2 over p, where p is the probability that the bones intersect a line. In other words, pi will be equal to 2 divided by the fraction of bones intersecting lines out of the total number of bones we cast. So how in the world does pi, the circle constant, get into a problem having to do with the probability that a needle, or in this case a bone, intersects a line on this array of lines? Well, as I said, I'm not going to go through all the detailed math. I'm not going to prove it to you. But just to give you a bit of intuition about it, it has to do with the angles between the bones and the lines. So, for example, this is one angle, this is a different angle, this is a different angle still, and so forth. In trigonometry, we represent angles in radians, which are always expressed in terms of pi. So, for example, 360 degrees is 2 pi, 180 degrees is pi, 90 degrees is pi over 2, and so forth. So that's where our sly little circle constant sneaks into this problem. It has to do with the angles formed between the needles or the bones and the lines. Anyway, because this is a probability-based experiment, if I only threw 1 or 2 bones, I wouldn't necessarily get very close to pi. In fact, if I threw just one, well, it either intersects or it doesn't. That doesn't really tell me anything about the probability. We need to do a lot of them. This is essentially going to be what's called a Monte Carlo simulation, where you repeat an experiment a large number of times, and what we should find is that if we do a sufficient number of experiments, if we throw a sufficient number of bones, our results should tend toward the true value of pi the more experiments we do. If I did just a couple, I might get close-ish to pi. If I did thousands and thousands or even millions or billions of experiments, I should be able to get pi to many, many decimal places. Now, I only have 18 of these little bones because I'm just using what I have lying around the house instead of buying any new ones. I am, after all, not a wealthy man, which incidentally is why y'all should like, share, subscribe, and buy my books so I can get filthy rich and start doing even crazier experiments. But that's neither here nor there. For today, what my limited means is instead of one really big experiment where I throw thousands of bones all at once, I'm going to do a bunch of tiny little experiments using these 18 bones. I'll count up the number of bones intersecting the lines out of each of the throws of 18, keep track of how many times I cast the bones, and use those sums to represent a large experiment. A bit of history before I begin. This problem was originally proposed in the 18th century by Georges-Louis Leclerc, Count of Buffon, hence the name. It was actually performed empirically in 1901 by Mario Lazzarini, who cast more than 3,000 needles and estimated pi correctly to, I believe, 6 decimal places, if I remember correctly. Frankly, I don't have that kind of time, so what I'm going to do is I'm going to cast my 18 bones a total of 42 times, because we all know 42 is the answer, and that'll give me a total of 756 bones, and then I'll calculate what proportion of those intersected the lines, and hopefully that should be enough to get at least a couple correct decimal places of pi. Here's hoping. But in case we are off, we can at least compare our empirically determined value to the known true value of pi, and we can calculate how close we got. For our experimental surface, I have prepared this sketch pad with lines, as I already showed you, spaced at distances equal to the length of those little bones. So the next thing you'll see after I finish talking to y'all will be a different camera angle looking down on this surface so you can see exactly how the experiment is going to work. Don't worry, I'm not going to make you watch all 42 castings of the bones and subsequent countings of the bones. We'll speed things up in the editing room, but I'll come back at the end with the results. So, introduction aside, I think it's time to get right to the experiment. All right, we are back and ready to go. Our experimental surface has been prepared. I've got the bones ready. I have a log sheet on which I can keep track of all the results. And when I'm done, I've got my trusty TI-84 with which I can calculate the final results. Just so that you're aware of how this is going to go, obviously that counts as not intersecting a line. That is intersecting a line. Even if it just hangs over the line by a little bit, we'll count that as intersecting. If it falls completely off the edge of the paper, I will re-throw that one. However, if it just hangs off the edge of the paper just a little bit like this one, because the lines are equidistant not only from each other but also from the edge of the paper, if it just hangs over the edge, I will count that as intersecting a line. So we're going to count the edges as a line. Hopefully that all makes some sense. So now what I'm going to do basically is just throw the bones around onto the surface, and then I will count up how many are intersecting and how many are not. So obviously this one is intersecting. Obviously this one, let's say this one here, was not. So I will do that. There's 18 bones here. I will do that with all 18, a grand total of 42 times, and then I'll tally everything up at the end. And I should also say, just to avoid any bias introduced by the way that I throw the bones, I'm going to try to sort of sprinkle them from above so that they fall as randomly as possible. Obviously, these bones are not uniform in shape. They have larger ends. That balance could affect the results a little bit. The way that I throw them could affect the results a little bit. This is not the most scientific of experiments in the world. I'm doing my best. We're going to work with what we got. All that having been said, let's go ahead and cast our first batch of bones across our paper. Dribbling them around as randomly as possible. They all stayed on the surface, and now it's just a matter of counting up how many are intersecting the lines. I'm going to pull them off as I count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This one's borderline, but I'm going to count it as 12. These other ones seem to not be intersecting any lines. So 12 out of the 18 intersected. I will record that here on my log sheet that there were 12. I will now repeat that 41 more times. I do believe it's time for a montage. All right, I've finished casting all of my bones. I'm back in my chair. I have the results here. I just need to add all of these up. I'm going to do that now. Okay, I've finished adding them all up. There were a total of 458 intersecting the lines out of a total of 756. That comes out to be approximately 458 divided by 756. 0.605 and some change. So now I just need to plug that into our original equation. And so we'll do 2 divided by that ratio, 458 divided by 756. And we will get, drum roll please, 3.3013. 3.3013 is our value of pi, which is obviously not quite right. We know that 3.14 is the true value, but there was a congressman back in the day who wanted to legislatively set the value of pi to be 4, I believe, or was it 3? Anyway, he wanted to manipulate it to be more off than our calculation was, so I feel reasonably good about that. Just do a quick calculation here and we will get... We were off by about 5.1%. So for throwing little plastic bones onto a hand-drawn array of lines and a relative few number of trials, 756 total, that's not too bad. I suspect if I did another round of similar magnitude, we would probably get at least 1 or 2 more decimal places correct, so for what it is, I think pretty good. And so all that really remains is for me to wish you the very happiest of Pi Days. Go do some math, go read or watch some horror, and if you want to do both at the same time, go check out my Arithmophobia, Anthology of Mathematical Horror, available at polymathpress.com or wherever books are sold. And of course, this being Pi Day, eat some pie. And as always, take care and stay scared.